Welcome back. It is so good to see you guys, or at least sort of see you guys. I guess it's kind of hard to think about when we're making a video, but I'm glad you are with me at least. All right, we're going to move now into calculations of pH and pOH. And we want to start with the concept of water. Now, remember I said that every substance has aqueous solution, has some amount of hydroxide and some amount of H+. I've already mentioned that those brackets mean molarity. So we're dealing in the concentration of units of molarity for this whole entire unit 13. Now, water, we saw earlier, could act as both an acid and a base. So if you look between here and here, these two species differ in an H and a plus, and it was a gaining of an H and a plus. Therefore, water acted as a base here. If I go to this one, water, just another molecule of water, in this case lost an H and a plus. So this water molecule acted as an acid. I'm going to introduce that term a little early. Substances that can act as both an acid and a base, we've got vocab a little bit later on, but it doesn't hurt to see this twice, are called amphoteric. I've also heard amphiprotic, so amphoteric, amphiprotic. Okay. Now, because water can basically, or effectively, I shouldn't use that word basically when we talk about acids and bases, it can effectively be both an acid and a base. It's called the self-ionization of water. And the mathematics behind it is that the concentration of H+, the molarity of H+, times the molarity of OH-, if we are at 25 degrees Celsius, is always 1.0 times 10 to the minus 14th. All right. Now, we could write H3O plus instead of H plus. I just can't get out of that habit of being lazy and writing H plus. But this is reality, is H3O plus. Now, note this is at 25 degrees Celsius, which is kind of interesting because pH is 7, and we're going to see how that relates to this in just a minute. But that's at 25 degrees Celsius. All right, and that's what we'll be focusing on. Now, let's do a quick review of what I introduced at the very beginning, because I presumed that you had some broad understanding of pH, but let's do it one more time just to make sure that we're on the same place. If my molarities, those really should have brackets there. If my concentration of H+, or if my number of H+ is more than my OH-, it's acidic. If my H+ is less than my OH-, it's basic. There's still some of each present. Now remember, basic is also called alkaline. If they are equal, we call it neutral. Now, here's the deal. Who wants to be working with numbers of 1 times 10 to the minus 14th? That just gets very awkward, very cumbersome to have to write over and over again. And so scientists came up with a logarithmic scale, a log scale. I'm not even sure I could spell logarithmic. I'm not going to try. We came up with a log scale, and it's base 10, log base 10, to make the numbers a little easier to talk about, a little easier to write. All right, so an acid is going to be anything that has 0 up to less than 7. Not equal to 7, but less than 7. Okay, a base is going to be greater than 7 and go up to 14. Now, I'm going to tell you right now, you can go below 0 and we can have solutions above 0, below 0 and above 14. But the most common substances are going to be between 0 and 14. Now, if it's exactly equal to 7, we call that neutral. So again, we're looking at that teeter-totter effect between my OH minus and my H plus. All right, so come here, straight line. There we go. So remember we looked at that earlier. We're looking at a teeter-totter that tips its scale right at pH 7. So depending on which we have more of, if the H plus is more heavily weighted, it's acidic. Okay, so that's kind of what we're looking at there. All right. Now, we can also talk about a pOH scale. Now, let's introduce that little letter P. What that little letter P means is to take the negative log of whatever follows. So we have pH means take the negative log of my H plus concentration. Okay, so let's see that in just a minute. So the pH is going to be minus the log of my H plus concentration. My pOH is minus, the little p means take minus the log base 10. OH means of my OH minus concentration. Okay. Now below 7 we have more acidity. Hopefully you know now from the video we watched that the reason that this is typically written as red is because litmus paper is red when it's acidic. Litmus paper is blue when it's basic. So blue, basic. The two B's go together. All right. Now, what that means, let's take a look at this. If pH is 1, that means that my H plus, let me show you how we can estimate these. If these are even numbers here, not 1.2, but just 1, my H plus, let me get a better color for you there, is 1 times 10 to the minus 1. If my pH is 2, my H plus is 1 times 10 to the minus 2. Do you see the pH just becomes the negative power? Then I'd have 1 times 10 to the minus 3 and 1 times 10 to the minus 4. I'm going to skip one because I'm out of room. 1 times 10 to the minus 6. So way up here, I have 1 times 10 to the minus 12. So here's the take home, a couple of take home that I want to show you here. Right? If there's a 1 in front, all you need to do is take the power. Drop the negative sign, take the power, and you have pH. If there's a 1 in front. If there's not a 1 in front, we're going to be doing calculations. Okay? But you can estimate. Now the other take home lesson I want you to see is this. Do you notice that H plus is small on that end? Well, that makes sense. It's basic. We don't have much H plus. And we notice that it's larger on that end. So as you increase the concentration of H plus, because it's a negative log scale, you decrease the pH. So the smaller the pH, the more H plus you have in the solution relative to your OH minus. Now, I want you to notice something here. Do you notice this is 1 times 10 to the minus 14th? Well, wasn't that my H plus times my OH minus solution or concentration? We just did that math, the self-ionization of water. So I want to try to make some links here for you. Okay. Now, this was just another graph that I like to show that we found online. Ms. Marusik found this and I just love it. Again, this shows that H plus. Do you notice that the power links with the pH? As long as there's a 1, there's an implied 1 in front of each of these, the power, drop the negative sign, there's your pH. Only if there's a 1 in front. Now, these are some common things that you're used to seeing. Our pop or our soda or our Coke, whatever you want to call it, is fairly acidic. Can be kind of bad for your teeth if you're not careful. Lemon juice is very acidic. And lemon juice tastes very sour, doesn't it? So if you kind of think of lemon juice as your classic acid example, it tastes sour. All right, baking soda could be our classic base. I don't know if you've ever baked cookies and maybe not mixed the baking soda in well, and while you're eating cookie dough, because of course we all eat cookie dough when we eat our cookies, you taste some of that baking soda, tastes very bitter. If you don't believe me, go take some baking soda and rub it on your tongue, and you'll see. These others aren't very safe to do that with. So I thought I'd kind of link that together while we were looking at this scale. All right, let's take a look at that self-ionization formula and analyze a couple of solutions here. All right. Well, this is just more qualitative. I have a beaker, all right, and that beaker is pH 4. I add a solution to that beaker, so I add another beaker to it. pH is unknown, all right, and I end up with a mixture of the two, and the pH is 5. Okay. So, what must have been true if we added these together? Well, if you increase the pH, that means we decreased our H+ concentration. And we do that by adding some base. That base would neutralize the H+. So this pH has to be greater than the original. All right, it must be at least less H+, so it dilutes out, makes the H+ less concentrated, or possibly even has some base added to it. Most importantly, it must be at a higher pH, and that means, let's backtrack, if it's at a higher pH, that means my concentration of H+ in this beaker is less than my concentration in the original beaker, and consequently my concentration of OH- must have been greater than my original beaker, right? Because if one is going to be decreased, the other has to increase. Okay, now same thing here. If I am above a pH of 7.5, if I want to decrease my pH, I want to increase my H+. Those are inversely proportional. To increase my H+, I add acid. Okay. All right. Calculations. Here's our little quadrant of calculations here. And from here we can get everywhere we need to get to go. The only exception is pH to OH- cannot be done directly. That is a two-step process. Now, if we're going to go around the block, doesn't matter whether we go that way around the block or this way around the block, it's still going to be 2 steps to get from pH to OH-. But these are your formulas. These formulas are also listed on your formula chart if the square is kind of confusing for you. But they're listed on your formula chart. And I just want to explain this a little bit, and then we will do some calculations next video. If I want to go from H+ to pH, pH is equal to minus the log of the H+. Now, if pH is equal to minus the log of the H+, let's just do a little algebra. Let's bring that negative sign over. Negative pH is equal to the log of my H+. The opposite operation of log base 10 is taking 10 to the power of. Now, that means we'd have 10 to the minus pH. Well, 10 to the log cancels out. So that's why H+ is 10 to the minus pH. Now, you notice we have very similar formulas over here. If I have OH- and I want to go to POH, pOH is equal to minus the log of the OH minus. If I have OH minus and I want to get from pOH, it's 10 raised to the minus pOH. Now we've seen this formula here, okay, and that relates to this one here. pH plus pOH is equal to 14. Well, look at that. That's if pH plus pOH is 14, when it's neutral, 7 plus 7 is equal to 14. Another way to look at it is when my H plus is equal to my OH minus, that's definition of neutral, right? I'd have H squared is equal to 1 times 10 to the minus 14th. The opposite operation of squaring is to take the square root. So x would equal 1 times 10 to the minus 7th. And that's how we get pH of 7. Okay, so hopefully things are tying together in your mind. I'm going to model a few of these calculations, and we'll do quite a few in class. So until next time, kiddos, this is signing off.